Last but not certainly not least is Arthur Mendes. He'll be talking to us about an LCL filter parameter selection using graphical method for a 13.8 kVAC 7-level flying capacitor converter. So a continuation of what we've been hearing from David and the rest. Arthur received his BS degree in electrical engineering from the Federal Center of Technology Education in Brazil in 2013. From 2011 to 2020, he worked at GE Power Conversion on medium voltage drives and utility scale inverters for solar and wind energy. He's currently earned his master's degree just last year in 2024 and is presently pursuing his PhD degree under Dr. Rolando Burgos. And his research interests include high power electronics and multi-level converters and renewable energy.
Thanks for the kind introduction. Hello, everyone. It's a pleasure to be here with you today and to talk about filter parameter selection using a graphical method for a medium voltage 7-level flying capacitor converter. We start with the introduction, a little bit of the background, the motivation, and some recap of the operation of the converter. And then we go through the method for selecting the parameters. And then we discuss what are the factors that affect the parameter selection, some examples and for comparison as well. And then we go to the result of the method. I believe David already laid out the application and the contest about this project, and as well as Professor Divan in the first day already lay out all the contests or all the challenges that we are facing with the grid, and energy flexible plant can be one of the solutions to provide grid support and also mitigation for curtailment in case of a lot of renewable, especially solar, connected to the grid. And to that end, this power conditioning system is proposed, and we have to connect it somehow to the grid, and that's why we use a ACU filter that has a couple of goals. It has to meet the standard requirements for power quality, which means the harmonic content on the current injected to the grid has to be limited, considering also that the grid is inductive in terms of power quality. This standard usually just evaluates up to the 5th harmonic. Second, currently there is no standard for the low frequency EMI. For example, the range between 2-3 kilohertz to 150 kilohertz conducted EMI, but there's a IEEE committee, SC77A, that is currently investigating the needs for regulating that in medium voltage. They have been working it quite a while, and so far we don't have much definitions, but a need for limitations and regulations for this frequency range was already suggested in several papers, including to utilize the same limits of, for example, a German standard BD EWE. The main concern here in this case will be the interaction with the mains communication, the power line communication, and also with this meeting. Also, we want a filter that can, or a filter design that can account for all the operation points and all the non-idealities of your converter. For this work, from now on, we consider extrapolation for frequencies above 50, the 50 harmonics, the extrapolation of IEEE 1547. So here's an example and a quick recap of the flying capacitor topology. We have cell 1 and cell 2 with each one with complementary switches that we have a modulation that is phase shifting between each other. That way the flying capacitor is naturally balanced, and the voltage is a fraction of the DC bus voltage. In case of a 3-level, it's half of the voltage. We see at the output switching frequency that is proportional to the number of levels, and the flying capacitor ripple is related to the switching frequency, but it also varies with the power factor of the operation. as can be seen in the waveforms. If you change from power factor 9, for example, to power factor 8, you're going to have more voltage ripple. And we have in this converter that David just presented, we have a variable switching frequency scheme that every time we reach a limit for the voltage ripple, we toggle the switching frequency to a higher switching frequency. But we just do that in a certain periods of the fundamental frequency. That way we avoid to increase the switching frequency too much. But this has some consequence to the filter design, which we are going to see soon. But before we go there, I would like to first introduce the method. So we basically, the main idea, the core of the method is to evaluate the filter transadmittance with the attenuation requirement that has the converter operation, the standard requirements embedded to it. So the main goal is to obtain the curve on the right side where the attenuation requirement is the red curve, and the filter could be a L filter or LCL or any other topology of filters, has to be always below the attenuation requirement, so you have the desired outcome. The filter is treated as a two-port network, and we analyze the transadmittance of it. While to obtain the attenuation requirement, we use the converter waveform, the voltage waveform, combined with what is the requirement for the application for the standard, and then we can have this plot. And you can see the result on the bottom part of this figure. We have the black dots are the harmonic content, and the green one is the limitation for the standard. So first we start by, how can we start that? We first start by calculating the maximum inductance. We come up with first with a simple L filter, so we can have a time domain simulation. And for that case, you don't need to have a well-rounded filter design. We just want a L filter so you can obtain the phase voltage of the converter. So, and that will depend obviously on your DC bus, which in our case is a fixed 22 kV, and also the implications of the rated current and the reactive power you're going to apply to the grid. Then you develop a time domain simulation where you can extract the phase voltage, and with that you can calculate based on your requirement what will be your current requirement, what will be your attenuation requirement, as you can see in red. It's usually more stringent when it moves downwards. Okay, but you can do that one time at a specific operation condition. But once you change the operation condition, for example, the power factor or the grid voltage, and you change the modulation, you're going to have different voltage waveforms. So it's necessary for you to sweep throughout all the operation conditions and obtain what it's called a virtual spectrum, which is pretty much the worst case scenario at each frequency bin of your attenuation requirement. As you can see on the figure on the right, all the dotted white dots, you have their operation with multiple power factor, and we get the worst case scenario at each frequency. That way, our filter design will work in all of the operation conditions of the converter, and not only one. And here's a couple of the factors that can influence the attenuation requirement. As you would expect, the number of levels in converter would offset the attenuation requirement. If you have more levels, you have a lower voltage THE, so obviously you are going to offset it upwards, and therefore you are going to have a smaller filter parameters. While if you have a 3-level, you're going to have a much more stringent requirement for your filters, and you have to have a large filter. So another interesting aspect of the method is it's useful to better understand how the parameters compare between two converters with different ratings. For example, In the right side, there is two 1.1 megawatt converters. One is for utility scale PV, which is usually low voltage but very high current, 690 volts and 1000 amps. And on the other side, you see our prototype, which is 13.8 kV, which is very high voltage but very low current. And in that case, you can see that the attenuation requirement is much more stringent on our case. So it's expected to have, let's say in a LCL filter, a much higher inductance and capacitance, for example, for even if you use the same modulation strategy and keep all the other parameters the same. But if you try to obtain the same parameters for the grid interface at full scale, you have a less stringent filter parameters. But that doesn't translate in size because, of course, then you're going to have a high current at the same voltage and also more losses, core losses, for example, but the parameters itself will be lower. So that helps you to understand a little bit more intuitive how the parameter varies. Another factor that affects the attenuation requirement, as I said, is the flying capacitor ripple. And as you can see, only during certain periods of the fundamental frequency, you have a larger flying capacitor ripple. And then the variable switching frequency scheme are targeted between 6 kilohertz and 3 kilohertz, as you can see. And that way, that affects the attenuation requirement on the right side. For example, we have in red, a curve that has no variable switching frequency with the same flying capacitors. We have increase of 17 dB in the attenuation requirement of the switching cell at the switching cell frequency. While if we have the variable switching frequency scheme, we at 300 volts threshold, we can lower that in 17 dBs. And then we have an example where in an ideal converter where there is no flying capacitor ripple, just as a reference. So if we also change the variable switching frequency threshold, we are going to change, obviously, the impact at the phase voltage and also the attenuation requirement. As you can see in yellow, if we increase the threshold, that means we are going to toggle less the frequency, and obviously we are going to get more flying capacitor ripple, and obviously the attenuation requirement will be much more stringent, as you can see on yellow on the right side. So, okay, we decided to go with a LCL filter because of we can obtain a better attenuation, but with a smaller filter. And here's just some recap on the transadmittance of the of the LCL filter. So we could, if we increase the filter capacitance, we are going to reduce the frequency, resonant frequency, and therefore we can benefit for higher attenuation. But if we increase the damping resistor, we could lower the damping, the peak, but at the resonance. But in compensation, we are going to lose a lot of attenuation at the high frequency, which is minus 60 dBs. It could be up to 50 or 40 dBs. So you kind of lose effectiveness of the filter. And also we could increase the inductance, then it's like shifting down the transadmittance plot, and also shifting a little bit to the left because if frequency, the resonant frequency changes a little bit, but then we have a bigger filter. But these are the parameters we can place so we can achieve the attenuation required. So, and you can see here the reason why we aim for the LCL, because at that frequency, for example, 30 kilohertz, for the same attenuation, with a single L filter, we will use a much larger inductance, and with LCL, we can benefit from a smaller filter. One thing that we have to be aware in case we're selecting the capacitance of the filter is that it is limited by the load capability of the converter. As you increase the filter capacitance, it will require more circulating current just to compensate for the power factor. Of course, if you change the inductance a little bit, that curve will shift, but as soon as you increase the filter capacitance again, you're going to require more current from the converter just to compensate for the power factor. And that can be calculated by the average model of the converter. There's a lot of papers that define that as a rule of thumb. So you select 5% or in PU, but you could just calculate that by the model of the converter. So we also have to establish other constraints. We already talked about the maximum inductance we can use based on the maximum voltage drop at the inductor, which will require, depends on the DC bus voltage, which is fixed 22 kV in our case. And also the maximum acceptable ripple will define what is our minimal L1 inductance. And as I just talked, the maximum capacitance will define the minimum value for your resonant frequency, because in case you have a very high capacitor, like I said, you're going to have a lower resonant frequency. You can benefit for higher attenuation, but you're going to have to circulate more current to your converter, and usually you don't want to do that. That way we have that design region. Sorry. Ooh. That way we have that design region where we can play with the parameters and verify the design. So the next step is to plot the attenuation curve of our condition and verify if we can get the attenuation required. So for example, right now we have the attenuation curve for our prototype. Then we can see, okay, if we use a L filter to attenuate up to the switching frequency, what would be the size of the filter? And also, if I want to attenuate only up to the flying capacitor ripple, what would be the inductance, which was much lower, but then we do not attend the requirements for the switching frequency. So that will be much lower in inductance, but we are not going to fully comply with the requirements. Then, okay, we can place this the resonant frequency as close as possible to the switching frequency, the combined switching frequency, but that is very difficult by keeping a low inductance, because then the flying capacitor ripple will start affecting your design, as it will be crossing the transadmittance of your filter. So you can try even to increase a little bit, but then you fall to the same problem at the switching frequency. So in that case, the best way is to decrease the resonant frequency of the filter by increasing the filter capacitor. And we can also verify if, okay, we are using those daughter cards to that David presented using low voltage capacitor that has 5% capacitance. What would happen if you have some tolerance? Are you going to cross the attenuation requirement? In case you do, then your filter won't may eventually not meet the requirement you established. So by following this, we are able to select the parameters L1 and L2 at 4 millihenry and the filter capacitor at 700 nanofarad with RD of 27 ohms. And as you can see on the bottom left side, the THD is 1.5%, and all of the individual harmonic spectrum is below the requirement. So as a summary and a conclusion, the graphical method for the AC parameter selection is proposed on frequency domain attenuation requirement. And the LCA parameters for our prototype is then selected compared with a full scale application. As I said, once you increase to the full scale application, 10 times the power, you get a much smaller parameters. And it's an interesting method because it can incorporate some practical design aspects and non-ideality of the converter design, such as the fine capacitor voltage ripple and also component tolerances. The method also provides an intuitive understanding of the filter requirements and performance, and can be readily iterate. Once you do it once, you can readily adapt in case the modulation strategy changes or the operation point changes. You can easily readily iterate and obtain a new design. Yep. Thank you.
Thank you, Arthur. Questions? So I'll get one start off since we still have a few minutes. Oh, here comes. We'll let him answer first.
Thank you. Alan Cooper, Diageo. When you're going through the process of selecting your capacitor, have you ever considered lifetime? The lifetime in terms of you've done the design, but how long it's going to last?
No, I haven't considered that, but this is something you could incorporate with the method, right? If you're talking about the variation of the capacitance along the lifetime, this is something you could add to the filter transadmittance plot and observe if that will cross your attenuation requirement curve. If that is the case, that means you need to change the model of the capacitor or eventually choose different parameters for your filter.
Yeah, I was just wondering if your models actually incorporated consideration for lifetime of usage in terms of the length of this thing is going to last, and whether you've considered that one in terms of your selection. That's all.
Yeah, so the way I see that, I would be considering that is by checking the variation of the parameters of the capacitor along time and how that influences the transadmittance of the LCL filter. If I do that like I did with basically component tolerance, then it will be the lifetime will be incorporated to the method. That's the way I see it. But I am not sure if you're seeing a different way of doing it that maybe I'm not seeing.
No, I'm not sure. I'm. It's just one of those things that people don't consider when they're actually doing the design. Is that we've done this design, it works. But then how long does it last? How soon have I got to change it and do all those sorts of things? I just wonder if you had a method for looking at the lifetime.
Yeah. So here mostly the main goal is to select the parameters for the filter first, and any lifetime considerations of the filter once you select it and start implementing the hardware. I think it would go with thermal cycling and operation conditions over time in a simulation. So that's not what the method proposed, but the method gives you the chance to verify once these parameters degrade with time, will the filter still be able to perform as you wish. So I think in that sense, the method considers the degradation of the capacitors.
Thank you.
All right. With that, let's give Arthur and all the other presenters another round of applause. Thank you. So now we're going to be moving into lunch, but please do remember to vote.